Okay, so first of all, housekeeping. You have an assignment due 5 o'clock on Friday. As always, if you have medical or compassionate grounds why you can't do it, I can organise 24-hour extensions. But if you hand it in late, remember you're handing it via Canvas, it will be stamped late. If it's 1 second past 5, you lose 40%. If you hand it more than 24 hours late, it's not getting marked, you get 0. Simple as that. So please remember that. What else do we need to know? We don't have a workshop this Friday. They're only on even weeks, but I will be in my room from 10 to 11 for like a consulting time. If you have any last minute questions or any concerns, please feel free to come. Also remember Mondays from 10 to 11 EMG 13, so that building over there at the base is yours to come and work together, do whatever you want. I will also be there from 10:30 onwards to give you any questions, especially with the coding aspect of this course. So please feel free to drop in and have a chat. Okay, so lecture 6. Let's see if this actually works. Woohoo! So, I don't know why I'm doing it because it's actually seriously a button there as opposed to a button there, but I just want to see if it actually works. So, we've looked at classification, we had some methods, and we've also looked at regression models. But right at the start, we talked about how do you know if your method's any good. And ideally what you want to do is you want to look at your test mean square error. So remember, your mean square error was the distance between your fitted model and your observations squared, added up, and you take the mean of that. And we talked about the test. Remember we had the train mean square error is when you calculate that on the training data, and then you have your test where you have a little test data set that you use it on. We talked about the fact that if you just look at your training mean square error, as your model gets more flexible, often that just keeps going down and down and down and down. And then we talked about the bias-variance trade-off, and the fact is you really need to keep some data aside that you can test your method on, because as you fit your method to that data, it gets better and better at predicting that data, exactly what we refer to as overfitting. So what you need is you need some other data sets. Say, look, I want my model to be good at predicting not just the data it's given, but future data sets. That's the whole idea of it. So how can we get an idea? How can we estimate this test mean square error? So today we're going to talk about cross-validation, etc. And then towards the end, we're going to look at something different with bootstrapping. So the first method you could do is what is called the validation set approach. So you get your data. Here it's represented by n data points, that white bar. And all I do is I split this, and I randomly split it, such that the blue section is data I'm going to use to train my model. But I've kept some aside, the validation set, that I'm not going to use to train at all. That at the end, I'm just going to use it to test my model. So the orange bar is the data I've put aside. So you've got your data, you put some aside, you don't touch it, it's never used in the training, you do your training, and then once you've finished training your model, you've got your best model, you go back and say, how's it doing? So here's the data we're going to look at. We're going to look at some auto data, which is part of the ISLR package. So what do we do? First of all, I've added myself, when you got the data, it had row names. Row names, just terrible, you get rid of them. No one uses row names nowadays. That was one of the key concepts of Tibbles. So I added myself a column. I converted them row names to a column called ID, because whenever you have a data set, it's really nice to have a column that just is a unique identifier for each row. Helps when you're messing around with your data. I set a seed for this year, and then what I do is I'm going to sample a proportion. So I've taken my auto and I've sampled a fraction. I'm going to sample 0.8. So 80% of that data is sampled, and I'm going to use 80% of my data as my training data. Then you may not have seen it before, but I'm doing an anti-join. What the anti-join does is it goes back to my original data set and says, find all the rows that aren't in the training data. So I've done an anti-join on ID. So what this has done is it's partitioned my data into two parts. The auto train, which is 80% of the data, and also the auto test, which is 20% I put aside. And no observation is in both, and I did that using the anti-join. Okay. So here's my lovely, lovely one-liner. Eventually I will get to a one-liner that goes over at least 3 slides, but I will still claim that it's a one-liner. So what am I going to do? I start with a vector of 1 to 10. Then what I'm going to do is I'm going to fit a polynomial. So I'm going to fit miles per gallon, which is my response variable, and also my predictor is going to be horsepower. So we're looking at the relationship between miles per gallon for cars and the horsepower of the engine. And all I've done here is the thing I'm passing into my map, the dot x, is just the size of the polynomial. So do a polynomial of size 1, so a linear, then a quadratic, a cubic, etc. The data, you can see I'm using the train data. Then what I do is for each of those models, so now I will have 10 models, I predict using that model with my new data, which is the test data. Then the next one is I've got a nice little map function that takes each of them predictions and it calculates me the mean square error. Finally, because when you give it the idea of the order, which will be the 1, 2, it thinks it's a character and it puts it in alphabetical order. So you actually get 1, 10, 2, 3. So I quickly say no, it's a number, put it in just to make my x-axis work. If you're not sure, just copy, paste the code, remove that line, see what it looks like. And then finally, I do my plot. So what do we see here? On the y-axis, we've got the mean square error for each of these models. And the first model is my linear, then my quadratic, my cubic. And the mean square error is basically the test mean square error. It's the deviation between the observed and the predicted for that data I set aside. Easy. Looking at that, what would you go? Which model would you go for?
Quadratic.
Why? Good answer, but why?
Because it's comparably low to all the other ones and it's the simplest model.
Yes, nice answer. So you're looking at that and you can actually see that you could just go blindly and say, well, I'm going to go for the minimum. This is one of the reasons you should always look at a plot. You could just go, let's get the minimum mean square error. You know that mean square error, you could just go which min and spit it out. And looking at this, it's either going to be 5 or 10. But we often do what we call a parsimonious type approach, which is we sort of want the smallest model we can get away with. So in this case, you're saying, well, yes, I get an improvement with 5 and 10, but not much improvement for my cubic, my quadratic. My quadratic is a nice, small, easily interpretable model. So very good answer. Still haven't got the chocolate frogs. You know 2 chocolate frogs.
That's fine.
Yeah, you say that, but chocolate frogs is chocolate frogs. So now, because we really like a one-liner, I just do all that again. If you don't know it, there's a really nice function called rerun, which will let you, yes, it will let you rerun a segment of code. All you do is you give it how many times. So I want to rerun 10 times. You can actually put the 10 inside the rerun, and you might say, well, why do you put it at the start? Just because when I come back to my code, the number that I want to do, the number of replicants is really obvious right at the start. Just makes it easier to look at. So for 10 times, I'm going to rerun this code. So what do? I go to my data, I partition it into a train and a test. Then I go and take that and I fit all these models, I get the mean square error. I then bind all that together and I spit it out. So I've basically taken that previous plot and repeated the whole process 10 times. Things that we notice. First of all, there's a lot of variability between these things. You know, at least one of these runs, you got a real increase in your mean square error as you got to the larger orders, that sort of royal blue type one at the top. Also, there's a lot of variability. If we, for example, focus just on, you know, the quadratic point, there's a lot of variability in that mean square error. Okay? You do get a lot of variability with this methodology.
They're also clusters.
Yeah, which is interesting. I don't quite know why. There must be, I haven't explored this, but you might want to go back and say, when it comes down to it, are you ending up with some other compounding factor that ends up being represented more in the training or the test? So when I've done my training test, I'm just randomly partitioning it. I'm not randomly partitioning it, taking into account other covariates. Maybe there's a blocking factor in this. Maybe there's like type of car, and you might want to do your partitioning within each of the blocking factors. You really love these chocolate frogs. That's good. Yeah, no, it's good. No, huge chocolate frog. So what are the concerns? So the validation estimate of the test error can be highly variable. Fine. So if you just do a single one, there's always this problem. Unfortunately, if you think about it, in this method, there's always data you put aside. More data means better estimates. You're always going to end up with this problem that, you're putting stuff aside, you are purposefully dropping information. So your method is never going to fit as well as if you used all the data. So how can we do it? How can we take this account? So the first one out is what we call a leave one out cross-validation. So what we do now we've got our data from 1 to n, represented by the white block. And what we do is the first time we go and we remove the first observation. And we fit the data on the remaining n-1 observations. You then go and predict what that first observation is and say, what's the error? You then go back to your data. You now remove the second observation. So you're leaving one out each time. You fit the data to all the n-1 except for the second. Then you use that model to predict your second observation and say, what's the error? And you do that all together n times. So you're going to have, for each observation, the error rate when it was the test and all the other data was the training. So here's the procedure. You're going to remove your data, your x, I, y. You're going to fit the model for remaining n-1 observations. You're going to calculate your mean square error for that individual point, which is your yi, its observed value minus the fitted, where it's the model fitted without that data point. And then your cross-validation, you average those.
So this is essentially jackknife.
I don't know jackknife, so yes, I'll say yes, as if I did know jackknife. I'll have to
It's
check.
just variance estimation.
Okay. That's labor intensive. You have to go and fit a model for every observation. The nice thing is, in the case of linear regression, there's a really nice shortcut. Show us the proof of it, Jono. No. You can prove it yourself in the next assignment. Because it's actually quite nice. So I'm going to give that as an assignment question for you to actually prove that relationship. But the nice thing is, if you think about it, you can now grab this data out very easily, where you take your fitted value and you're adjusting by your H index, which remember, your H index is x transpose x to minus 1, x transpose. So for linear regression, this is really fast. You can do it with just fit the model once and quickly spit out your cross-validation error. It's very nice. So taking that idea a bit further, because you've got this, I said it's really fast for linear regression, but we're advanced data science. We're now going beyond linear regression. Other techniques, it is going to be expensive. Fitting a model n times 1 for each data point, especially when we're going to hopefully start getting data that can have things like with the taxi data set, if we can get it working, we'll have 3 billion observations. Even if your code's really, really good and your linear model is, well, not linear model, but your logistic regression, say, only takes a second, that's still 3 billion seconds. That's quite a bit of time. So then the next thing you can do is say, well, we like that idea. The sort of idea that you take some data aside, you fit your model, you use the data you set aside as your training to get your mean square error, but then you put it back in, and combining these results, so all the data is used eventually, but we still have a estimate of our mean square error is a good idea. So next one is the k-fold cross-validation. So now what we do is we take our data, the white bar, and we split it into k pieces, roughly of equal size. And the first thing you do is you remove the first piece, which is my orange block there. That is now my test data. I put it aside. I fit the model on the remaining k minus 1 pieces. And then I work out my mean square error for the piece I put aside. Go back to the data. Now take the second piece, take it out. So you partition the data, you take each piece out one at a time, you fit on the remaining, and then you see how good it's doing. So there's a procedure. Partition data into k parts, for each part fit the model in the k minus 1. Use the fitted model to predict for the part removed. How do you calculate? So here's the notation. We'll let our k parts be indicated by C1 up to ck. There are going to be nk observations, and obviously if it's your n, your total number of observations, is a multiple of k, then nk will just be n divided by k. That's not always possible. You know, if you're doing a fivefold, if it's not a multiple of 5, you might end up with a slightly smaller one. What we do is for each particular block, that's our test block, when we put it aside, you work out the sum of all the observations minus their fitted value, where it's fitted on the piece, on the k minus 1 blocks you hadn't used. You add that up, you square it, you divide by n minus k, and then finally what you're going to do is, if you've got k blocks, you're going to end up with k MSEs. You then combine all those results together using a weighted mean. So let's go through the code just to get an idea of how you can do this. So I'm going to use the modeler package, which gives us some very nice built-in stuff. So what I do is I take my data, I say I want to do cross-validation k-fold, I want k equal to be 5, and then what this does, and it's one of the reasons we've done nested data frames, is it spits out a nested data frame structure. One thing, there's a trick with this. It's created, you can see first of all, it's got altogether 5 rows, and each row it has the training data and the test data. I'll show you in a second. There's a trick. You have to be careful because it's actually created what's called a promise. It hasn't actually gone and taken them bits of data frame and squashed them down and put it together. That's memory dense. It's actually got a list of indexes for them. That makes no difference to anything you do. You wouldn't even realize you're doing it until later. There'll be one line I show you, and what that does is it forces it to change that promise, which is indexes, and actually convert it to a data frame. Otherwise, you find if you run the code about that line, it crashes. It just sort of goes, I can't do what you're asking, it's not a data frame. Because at the moment, because it wants to do memory storage, it's not got a data frame, it's basically got a list of the rows that would be in that data frame. Okay. So now we've got all our map functions. So the first thing I'm going to do is I'm going to fit 2 models. I'm going to take my auto CV. Inside that there'll be a column of train. I'm going to map for each of them training, so that's going to be a whole series of data frames, my training data frames. And I'm going to fit a linear model of miles per gallon on horsepower. The second model I'm going to do is I'm going to do exactly the same. I'm going to have horsepower plus the quadratic. So now you have 2 lists, M1 and M2. And M1 will be a mixture altogether, 5 models, where I've taken the k minus 1 parts and I've fitted a linear regression. Now I'm going to get a prediction function. This function is going to take a model and some test data and just return me the data frame with the predictors. Notice that second line in my function where I go data equals as data frame test data. That's the line which forces, the moment test data, when you pass it, is just a load of indexes. It's a promise. And that's the line that actually says, no, now's the point you need to convert that promise into a data frame. It got done automatically for you before. When you fit models, R is clever enough to go, fine, do it. When you get to this point, you just have that single line. And if you're not sure, remove that line, rerun it, and you'll see it just crashes and just says, I don't know what you're doing. That line says, at this point, take that promise and convert it. I'm caching it in, give me the data frame. So what do? I take my test data, I add the predictions using the modeler R. To add predictions, you give it some data and you give it the model. And what it will do is it will add an extra column with your predictions. So now I just do a map to df. So you've got the map functions. Map to will take 2 lists. And it will go to the first element of both lists, apply it. Go to the second element of both lists, apply it, etc. So with this one, I give it my list of models. I give it the list of tests that go with each model, and I say do that and give me my predictor. And I'm going to do that for both lists of models, for the linear and the quadratic. And when you have a look at it, you can see it spits out your data there. This is run 1, it's got all the information, and the final column is that nice predictor ready to go. So now we're pretty well there. We can just group by each run. We can organize a summary where the mean square is going to be the mean of the MG minus the pred, all squared. If you haven't seen it before, n equals n bracket bracket is a shortcut you can use in summarize, which will just count the number of rows for you. It's just a quick shortcut for counting rows. So when I spit that out, you can see for the first set of predictors with the linear model, there's my mean square error and the size. For my second one, my mean square error 2 for the second, which is the quadratic, you get them. And then finally, I can just do my calculation of my weighted mean. And we have our two models. Which model are you going to choose?
The quadratic.
Why?
It's got a smaller.
Yeah, exactly. Don't forget, we want the MSE to be small, so the quadratic is the smaller one. Which agrees with everything we saw before. It passes the consistency stupidity test, so we're happy. Okay, so let's think about these general things. First of all, bias-variance trade-off. The validation method tends to overestimate the test MSE. We do find that it's, it does, and I haven't mentioned this, mainly because it's not in the textbook, and I see it rarely, but some people will actually do a combination of two. They will get their data, if they have enough data, they will take some out, which is their final validation, put that aside, go back to the remaining data, now do k-fold cross-validation on that, and then the very final point, once they've finally decided on their final model, they do a final test MSE on that. I know of it. I've never done it myself. I have heard of people that do it. It seems to be a little bit of I wear a belt and braces at the same time sort of thing. But if you have enough data, fair enough. But anyway, so validation tends to, the leave one out cross validation tends to give unbiased estimates to test MSE. That is really, really good because you've got as good as you can get. It's like the K in your K-fold equals N. Well, your K-fold CV lies between the two. The problem with your leave one out cross validation is it has a higher variance. And let's think about why that happens. Is every time I calculate my mean square error on that individual point, there's a lot of overlap between the variables that were used in the predictors. So the models are very consistent with one another because at each point, if you think about your first point, you take your first point out and you've fitted your model using the final n minus 1 points. In the second cross validation, you've introduced a new point and you've lost a new point, but the model generally had n minus 2 observations in common. So all your models are very highly correlated in terms of the coefficients. And because they're highly correlated, you'll find their predictions are highly correlated. Therefore, the mean square errors are highly correlated. And we know if you think about means of highly correlated variables, you've got all them covariance terms you have to add in. Remember, the expected value of a sum of random variables, normally we'll happy and go, oh, they're independent, that's fine. And you just sort of add up your variance terms. No, now you've got lots and lots of covariance of things that are highly correlated. So you do have that problem. And as a rule of thumb, people seem to be, and the textbook recommends this, that a k-fold is probably the best using 5 or 10. You've got to weigh that with your computation time. If you've got linear regression with the thing you're going to prove, the fact you can do one single fitting and it's done, leave one out cross validation would definitely be a good thing to consider. What do we do in classification problems? Well, we just need some sort of error rate, and we come back to this idea that we're just going to count our error rate using an indicator function. So we'll go and fit our model, and then we'll just say, did you get it right or not? And we count up the average number of rights and wrongs, where 1 is a mistake and 0 is you got it right. Now we're going to talk about something slightly different, the bootstrap. Okay, So I'm going to motivate this with a nice simple problem. Here's some data. I've randomly simulated some data, and there's my histogram of the data, and I find the sample median is 0.6502143. Okay. So if it was a sample mean and I said do a 95% confidence interval, you should have no problem. You go sample mean plus or minus, let's assume I know the variance, 1.96 times the square root, and then you do sigma squared over n. Because you know the asymptotic distribution of the sample mean, especially under assumptions of normality. And if the data was big enough, you could just sort of use the central limit theorem to still get your 95% confidence interval. So you have this, what we call pivotal distributional quantity to do it. So what's the asymptotic distribution of the sample median? And that's this is a simple thing to do. People want the sample median. House prices, sample median. Anything that's very right skewed, sample median. It'd be really nice if we could get a 95% confidence interval for that. But the problem is there's not often a nice distribution to get it. There's not like a central limit theorem for medians. So how are we going to do that? We're going to do it with the bootstrap. So okay, setup. Suppose we have a simple random sample. So this is our data S, and it's x1 up to xn. And we have some statistic t, which is a function of our data, which is an estimate of the population parameter. So in our case, our population parameter would be the population median, and obviously the way we did it is we calculated the sample median. You ordered them, you took the middle point. And what we'd really like to know is we'd like to know the sampling distribution of t. So in the case of sample mean, we knew the sampling distribution was normally distributed with the mean of mu and a variance of sigma squared over n. But we're going to get an empirical one. What that means is we're going to use the data itself to give us that distribution. So by empirically, I mean I'm going to go back to the data, I'm going to use that to give me the sampling. And we use a method called bootstrapping to do this. So how do we do this? What I'm going to do is I'm going to repeat the process b times. And what I'm going to do is I'm going to sample with replacement a sample of the same size from the original data. Obviously, you can't sample without replacement, because if you sample without replacement a data of the same size, you will get exactly the same data. What it does mean, think about it, is some points in the original data might get missed out, and there's a good chance that some points will get there more than once. So you go to your data and you just go and say, right, I'll keep grabbing it out, put it back in, grab it, and just record until I get a size of sample m. And so I'm going to denote the B sample as SB star. So I've got n observations. Some of them might be repeated observations, but it's the same size as the original sample, and it was obtained from the original sample by sampling with replacement. And then all I'll do is for each of these new data sets, I compute the value of this statistic. So I go to my first one, I calculate sample median, go to the next one, sample median, etc. And we'll denote that as TB star. So the B indicates which sample it's from in the bootstrap, and the star is just to remind me that I've done the bootstrapping. And here's the key idea. The relationship between the population to the sample should be the same as the sample to the bootstrap sample. So it's like you've got this population and you went, look, I know if I take a sample, it's representative of that original population. And the idea is now is by sampling, now my sample becomes a population, I sample from it again, and the relationship should be roughly equivalent. So the distribution of TB star around the original estimate T is now, I'm never going to be able to say that word, is similar to the sampling, I should learn to speak quite properly, shouldn't I? But it's not going to fucking happen, is it? Great accent for starting a fight, not so good for doing fancy stuff. So that relationship should be the same as the sampling distribution of the estimated T around the population parameter. So you know, if you had your parameter right in the middle of the room, sorry for everyone who's listening to this line, and I have this nice, beautiful, normal distribution around me, then I've taken a single, I've got my sample mean, that distribution around me now, they should be similar. And now I've got this set of summary statistics. I can start, if I want the mean of it, I just take the sample mean of my summary statistics. If I want the variance of my bootstrap, I just take the sample variance. And also you can actually measure the bias. In this case, the bias will be the sample mean from my bootstraps, take the original value. And that bias we're going to use in one of our confidence intervals. But the thing we want is confidence interval. First of all, you can do the bootstrap percentile. That there is the absolutely correct notation for the bootstrap percentile. But all I'm really saying is you take all your bootstrap statistics. If you wanted the 95% confidence interval, you would order them and you would find the point such that there is 0.025 of the observations to the left of it and the point such that there's 0.975 less than it. So you just use your quantile function. Notice the normal theory interval is slightly different. In this case, they automatically do a bias adjustment in their 95% confidence interval. So you've got your usual, the first bit looks almost right. You've got this t minus b hat t theta, but then they do plus or minus z alpha on 2 and your standard error. I'd never seen this before. I wandered around the building and asked people cleverer than me, and they'd not seen it before. And then eventually I found a statistician that went, yeah, of course, it's standard. And what is, what? No, it was Mel. In fact, Mel laughed. I went, oh, yeah. She goes, but she got her notes out and said, here's the notes. And I went, oh, cool, they're really cool notes. Where they're from? She went, oh, yeah, in UTAS we teach it in second year. I went, well, we teach it in honours. Oh, we're a little bit late. But yeah, so it's an automatic bias adjustment. So instead of just going, here's my sample mean, plus or minus my margin of error, they go, let's do the bias corrected sample mean, plus or minus the error. Cool. So let's actually do it. So first of all, we'll do it by hand, and then I'll show you that there's actually a built-in bootstrap to do it. So first of all, what's our observed data? We've got our data, and it's got a column called X, which is our observations. So our T observed is just the median, and it's 0.6502143. Then I use the rerun. This time I'm going to rerun it 10,000 times. What do? All I do is I take my data, I sample, put replace equals true, so that just goes and gets me a sample of the same size as the original data with replacement equals true, and I just take the median. And that was my bootstrap in that one line, and then I unlist it because that will return a list, and I want it nicely in just a vector. So you can see here are the first 10 sample medians where in each time I went to my data, I sampled with replacement the same size, calculated the sample median, stored that. That is bootstrapping. To get my confidence intervals, you could quickly take your t-star, which is all your 10,000 observations, and say, return me the cutoff points of my quantiles, the 0.025 and 0.975. So we are 95% confident that the population mean in this population lies between 0.4948 and 0.9585. I happen to know that the true population for this data was 1 over root 2. You can check that because it was a exponential with a rate of 1.
Can we ask on the previous slide, how does sample choose how big the sample is?
Because sample has a default behavior, good question, that you can actually say the size of your sample. If you don't, it gives you a size of the sample equivalent to the original size. So they built it that way so it could be an automatic permute function as well. So if you don't put in, if you'd put sample comma size equals, you could choose different sizes. The default behavior is to return a sample of the same size. And I just used it like that.
The same size as the data set?
Yeah.
Aren't you sampling from the data set?
Yes.
Then if you're taking a sample of the same size as the data set from the data set, aren't you getting the data set?
Not if I do replace equals true.
Place
So,
I'm sorry,
okay, let me explain. So you've got, let's say I had 10 observations. Yeah?
Yeah.
And I want to sample a list of 10 observations. If I would put replace equals false, I will get exactly the same data back, yes?
Oh, so you get repeats. Right,
So
okay.
you take them one at a time.
Yes. And so you replace it. So
Yeah.
that's what I was trying to say before, obviously badly, is that some observations will end up being in the sample more than once.
You can think about it like generating random numbers, right? That are integers between 1 and the size of the sample. And if you're generating random numbers, you're going to get the same one sometimes.
Yeah.
Yeah. Okay.
Yeah.
But I thought it was sampling a subset. But
No, exactly the same size. So it's representative. So there's my quantile, and there's my normal calculation. I calculate the bias, so the mean of my observed sample medians minus the actual value I got. I did the variance of that, I did the square root, got the standard error, and there's my calculation. So you can see the two.
So the thing with the information thing, blah, blah, blah. So all we're doing there is actually that's because it's T-obs minus the bias. All you're doing is return the mean of T star.
No, it's 2 times that. I thought exactly the same. If you actually write it out, when you minus it off, the minus becomes a plus.
Yeah.
And don't worry, I made that mistake, and I thought I was an idiot. But then Nigel Bean made that mistake, so I'm not an idiot. I've been Bean classified.
That's not what the math says.
No. It does. Seriously, think about what the bias is. The bias was the T star minus T.
Yeah.
And then I think if you do the calculations right, you get an
yeah,
extra.
yeah.
Good point, though.
2 T-obs minus the mean.
Yeah. And when you look on Wiki, they have this weird thing where they have this 2 T-obs, and you're like, where's that 2 come from? There's been a whole thing of me wandering around buildings being an idiot, and then other people who are more important than me also being idiots, and then we all wandered around until Mel just went, but we do that in fucking second year, and we all went, oh. Like, it's not about going, this is hardcore stuff. We nailed this together. And then Mel went, but we teach that in kindergarten. It was a bit. Cool. Does that all make sense? It seems to be a con, and I believe it might be a con, but it's a very useful con. Like, let's face it, you took your data and you just kept sampling until you sort of went and da-da, and there is a sense of like, what? But it's a standard technique, and it's really good for those tricky statistics you don't have. Keep it in your tool bag. It's really, really useful.
It's get used a lot.
Yeah, bootstrapping gets used up. Very computationally expensive. That's the main problem, but very, very useful. And there's actually a package, which I didn't put here, which I do apologize, called the boot package, which will do it all automatically. It's a little bit tricky. This is one of the few times when my implementation, I think, is slightly easier to understand than their implementation. Because to do the bootstrap method, you have to create a function. You can call it whatever you want, but I call it statistics. That fits in with their notation. Which the first thing we'll take is data, and the second thing is index. Right? So what you're doing is you're creating this generic function that they're going to use, and they're going to pass the index in for you when they do the sampling. So what index does is it says it's going to be a vector of the same size as your original data that's going to say which of the rows are you going to select. So now what I do is when I take my data, and when my data, I'm going to select the rows indicated by index. Index is going to be the integer vector, and then I'm going to return the median of the data of x. But it does seem strange because when you first start writing, I'm always like, I've got an argument here, I don't know, I never use it, you never see it. And it's because Bootstrap assumes that your function will have 2 arguments when you pass it in. One will be called data, and one will be called index, and it will be set up that you inside that will do that sampling for it and create. So your statistic should do the sampling and the calculation statistic and just spit out a single number. Once you set it up though, it's very, very nice. There's a function called boot, you give it the data, you give it statistic, and you say how many replications you want, the same number of replications. It's fast. It will probably always be faster than your implementation because I think it does actually underneath the cover speed things up a lot. But then it removes an object called data boot. And when you actually look at that, it tells you information already about the original value, the bias, and the standard error straight out. But also as well, it has a thing called boot.ci, and you can give that and you can ask for lots of different confidence intervals and it spits them out automatically. Remember, my intervals and its intervals will not necessarily agree. They should agree in size, etc. But all this is based on sampling. So their data, you can't get the data they sampled out, but you can get all the individual statistical values out as well if you want to. As I said, it's not the nicest package I've used. It's a bit of an old school one, and I think that setting of the statistic makes it hard. And there's a lot more stuff you can change as well. So that's it. That's cross-validation and bootstrapping. And I think next week we start to look at regression and model selection, things like Lasso, Ridge, etc. Any questions, as always, come and see me. If not, I will see you either in consulting or next Monday. Thank you very much.
Nice. Every slide of data